Good morning. Please take your seats. A few more people are filtering in, so I'll give it just a second. But I think we're mostly here. Welcome. Those of you who don't know me, I'm Vince Poor, and on behalf of my co-chair, Jong-Seong No, who's sitting here, I'd like to welcome you to Seoul and to the 2009 IEEE International Symposium on Information Theory. Also welcome you on behalf of the entire operating committee who have done a tremendous job of putting this meeting together. I have one announcement, and then I'll turn the podium over to Rob Calderbank. For those of you who have accompanying persons who'd like to meet up with one another, there's a room, the VIP room, which is in room 203A here in this COEX. And beginning this afternoon and the rest of the symposium, there'll be coffee and pastries and cookies and so forth there. So any accompanying persons who would like to meet up with others is welcome to join there. So that's room 207A. We'll probably put an announcement out in the lobby sometime today. Rob and Haebong Chung and Alon Orlitsky, the technical program chairs, have put together an outstanding program. I think you'll all enjoy it, beginning with this morning's plenary speaker. And so I think with that, I'll just turn it over to Rob, who's going to introduce the speaker this morning. So again, welcome. Hope you have a good week.
Well, again, we seem to have stopped filtering in. I was going to introduce Rich by talking about different inventors. So Alexander Graham Bell invented the telephone, Marconi, AM radio. And the question is really, what did these guys have in common with Rich Baraniuk? Anyone have any idea? Let me give you some more clues. James Naismith invented basketball. What does he have in common with Rich Baraniuk? Yes, I heard the answer from the audience was that they're all Canadians. They're examples of famous Canadians. Now, the other two people on my list were James Carey and Pamela Anderson, so I'm glad I didn't have to go there. So Rich completed his undergraduate studies at the University of Manitoba in Canada. He got his PhD from Illinois in 1992. And for the last 15 years, he's been mostly at Rice University, where he's the Victor E. Cameron Professor of Engineering. He has a rather broad reputation for innovation. About 10 years ago, he launched something called Connections, which is a somewhat subversive, non-profit publishing project that aims to bring textbooks and learning materials into the internet age. That's not what he's going to be talking about today. Today, the subject is really, well, there's a lot of excitement around detection and estimation today. I think not because of where we are, but because of where we might be going. So we used to live in a world where it was hard to collect data. And I think that's reflected in a theory of detection and estimation which emphasizes very sophisticated mathematical models and a fascination, maybe an unhealthy fascination, with maximum likelihood detection. And we no longer live in that world. So we live in a world where we're drowning in data. And there's a lot of excitement about creating a new theory of detection and estimation where it's the geometry of data that's important. And today, Rich is going to open the door on that world. So please join me in welcoming Rich Baraniuk.
Can everybody hear me okay? Okay, good. I might be from Canada, but I am the reincarnation of Michael Jackson. At least I feel like that with this microphone. It's really great to be here today speaking about some of the work that we've been doing and others have been doing in this world of randomized dimensionality reduction. I would like to thank both the organizing committee and the technical program committee for the opportunity to speak today. And I also appreciate that all of you who got up, maybe some of you much easier than others due to jet lag. My job today is to talk a little bit about what this field of randomized dimensionality reduction and compressive sensing is, give you a sense of where it's been and really where it's going and what some of the interplays are with the field of information theory. And I'm just going to mention that Rob is going to keep me on time today, because I find that whenever I fly somewhere, I always speak about 9% slower than I usually do. So hopefully we'll get through everything today. Okay, so if people hadn't noticed, there's been a digital revolution in the world around digitization of all kinds of different data sources. And this has resulted in an absolutely, as Rob was saying, an absolutely unbelievable explosion in the amount of data that is being generated every year. Okay, just to give you some quick ideas, in 2007 alone, we generated over 200 billion gigabytes of data. Okay? And that amount of data is growing by a factor of 10 about every 5 years. So in about 15 years, we'll generate more data per year than Avogadro's number. Okay? And the growth of this amount of data is really due to really the digitization of all kinds of different multimedia data streams: audio, video, still imagery, camera, surveillance networks, etc. But the last point is the one that I really want everybody to focus on, and that is that 2007 was a watershed moment in that for the very first time, we actually generated more data than the entirety of all the world's storage. Okay, that's very, very important, because what that means is we're now in a regime where in a great many applications, it is never going to be possible to be able to store our data in some data warehouse, revisit it later to make some kind of decision or to do some kind of analytic. It's going to be absolutely critical that we start to work in real time with our data and that we are able to triage the amount of data, because what's happening is that the amount of data explosion is actually growing at a faster exponential rate than Moore's law. Okay, so that's really what today's talk is about, are some ways out of this difference between the exponential growth curves of the generation of the amount of data and Moore's law. So we're going to talk first about what's wrong with how we do things today, right? What's wrong with the current ways that we sense and that we compress and that we process. Then we're going to talk about one potential way out, and it's this idea of using dimensionality reduction as close as possible to the head end of a sensing system, okay, as close as possible. And we'll talk about the theory behind that in some detail, but then some elements about the practice of how this is actually being used today in a number of different groups around the world. And then finally, time permitting, I will talk as much as I can about some of the really interesting synergies with the field of information theory and coding. Because, of course, since this is about signal analysis and processing and representation, really it is all about information theory. And let me just ask a quick question to the organizers. Do we want to have questions as we go? I have no problem with that. Is this room okay? Okay, so maybe we'll hold the questions at the end, so hopefully you can remember. Okay, so just very, very briefly, let's just talk about the standard paradigm that people have today adopted for doing signal analysis and signal processing. And let's just imagine we're going to take a picture of Nicholas over here. So we get out our trusty digital camera, and then guided by Shannon, we know that we have to sample at 2 times the highest frequency in that image. And from that set of samples, we get n pieces of information, right? So there's n pieces of information. In a lot of different cases, that's way too much data. Okay, again, thinking back to this explosion of the amount of data. And so we invariably think about doing some kind of either processing right at the head end of the system or some kind of compression. And let's just think of the compression idea for a second. We're basically taking our n pixel values in this case and running them through some kind of algorithm to crunch those n numbers down to just k numbers, right? Where k is hopefully much smaller than n. K numbers, real numbers, and then eventually some number of bits. And this is the information that we store on our camera or that we transmit over over the ether with our iPhone. And of course, there's a complementary decompression process where we get the picture of Nicholas back at the end. And this is, I think this isn't, it goes without saying that this is absolutely paradigmatic of today's view of signal processing. So the fundamental mathematical structure that underlies any of these kind of compression algorithms related to multimedia data is this idea of sparsity. The idea that I can take my n pixel image and I can re-represent it using an orthogonal transform, for example, a wavelet transform in this case, and I don't change the information content, the amount of information. What I do is I just rearrange it so it's organized in some different way. And what you can see on the right here is by taking a wavelet transform, we have basically compacted the information in that picture of Nicholas into just a very few, a small number of large wavelet coefficients corresponding to the edges in the picture of Nicholas. And then all the rest of the coefficients are blue in this case, which corresponds to 0 or very small. And so the essence of transform domain compression is to acquire data, compute an orthogonal transform, and then throw away all the small coefficients and keep just the k biggest coefficients. So when this is true, we say our data is k sparse, right? It has k large entries and n minus k small entries. Of course, in practice, I'm not going to talk very much about this in the talk, but of course in practice, real-world data isn't exactly sparse. It's approximately sparse. Right? There's some fuzz there in the blue coefficients, but let's leave that until the very end of the talk. You might think that this is a very special property of imagery, but in fact, I would argue that this is actually a general property of hordes of man-made and natural data. Here's just one other example. Take a chirp emitted by a brown bat as it flies through the air, echolocating to find yummy moths. This is a signal that has a very wide time bandwidth product, meaning the pulses are very long in time, and when you compute their Fourier transform, they're very broad in frequency. So they require a very high sampling rate. But if we re-represent the data in terms of a time-frequency representation, like a spectrogram, or in this case, a Gabor transform, you can see using that same color map, again, we're extremely sparse. Most of the coefficients are 0, and just a very few, you can see at any given point in time here, there are just 3 harmonics, right, that are active in this signal. So again, very, very sparse data. And this is what enables us to compress a lot of audio and other acoustic type data. So there's 2 things wrong with this process, right? The first is, why do we go to all the work to get n numbers back to our digital camera, right, n pixel samples, in order to throw away all but k numbers at the output of the compression algorithm? It does seem a little bit wasteful, at least from a sensing design standpoint. The second, and that I would argue a much more fundamental limitation of this kind of approach, is that there's a complete disconnect between the idea of Shannon sampling, right, which is based on a completely linear theory. Right? Band-limited signals form linear subspaces. We acquire them by uniform samples, which is a linear operation, and we reconstruct analog signals by sync interpolation, which is again linear. It's a completely linear theory. Okay, trying to combine that with this theory of transform domain compression, which is, other than the transformation, for example, into the wavelet domain, is an extraordinarily nonlinear process. Right? This process of taking a transform and throwing away all but its k largest coefficients is extremely nonlinear. And as we'll see, the signal model of signals that can be compressed effectively is, again, an extremely nonlinear model. So what we're trying to do when we do sample and then compress is that we're trying to put together, right, something totally based on a linear theory with something based on a much highly nonlinear theory, and it's not clear that the combination is in any way optimal. So that the idea of dimensionality reduction, as it comes into this then, is to try to build new systems for data acquisition of all different kinds of data that instead of sampling and then compressing, somehow do everything all together in one fell swoop, where we go directly from, for example, the analog light coming into our camera, and we directly produce what we'll call measurements, which is really an encoding of our signal. And with the idea being twofold, that first, we can actually recover our data from those M measurements. So there's an information preservation property. And second, we can push the number of measurements M very close to K. So that in our sense, we're getting very close to the same performance as if we were to sample first and then compress. And that's really the basic ideas behind what I'm going to be talking about today. So let's just go briefly for about 10, 15 minutes into the theory of why this works. And I know a lot of you, let me get a show of hands. How many were at Emmanuel's fabulous tutorial yesterday? Show of hands. Okay, so maybe a third, okay? So for those of you who weren't there, we're going to review some of that material. And for those of you who were, we're going to put slightly different spin on some of the ideas to bring up some of the connections later. So let's talk really, really briefly about a very simple model for sampling, an oversimplified model for sampling. And let's say that my signal x is k-sparse, right? And let's say it's k-sparse in the canonical domain. What do I mean by that? I mean x is a length n discrete time vector. Think of n as very long, millions or billions. And there are just k non-zero entries, in this case 3 non-zero entries in this very, very long vector. And this vector is sparse in not in the wavelet domain or the Fourier domain, but in the canonical domain, which if this was a time signal, it would just look like a long string of zeros with 3 spikes in it. Okay? We'll talk about generalizing this in a minute. And second, I'm going to start directly with discrete time signals here rather than analog signals. But you could also think of, instead of this being n samples of n discrete time samples, you could think of this as n Nyquist rate samples, or the coefficients of an n-dimensional subspace representation of a band-limited signal. But let's just think of x as a discrete time sparse signal. So what do we do when we sample? Essentially, we're multiplying x by an identity matrix. And this identity matrix we're going to call phi. It's the sensing, we're going to call it the sensing matrix. And why is this a sampling matrix? Well, since each entry of y is just the inner product of that corresponding row of phi with x, you see that the entries, each row of phi, is just a delta function. And these are just marching delta functions that pick off samples of x. And obviously, since phi is equal to the identity matrix, from y, we preserve all the information in x. This is clear. And it's trivial to reconstruct x given y. Okay, so this is Rich B's very oversimplified view of sampling. Okay, we're not going to do this, though. We don't want to take n samples. We want to build systems that rely on some kind of dimensionality reduction, where the number of measurements, or the length of the encoded version of our signal, y now, is going to be m, and m is going to be much less than n. So now our matrix isn't going to be square. It's going to be really short and really fat. And it should be obvious to you that you can't just pack delta functions into this matrix and hope to preserve all the information in x in y. Okay, so this is the setup. Okay, and so let's talk about this really briefly. So this setup sounds a little bit problematic because phi is a rectangular matrix, so there's no way it's full rank. It means it has a null space, which means it has to lose information. Okay, what do I mean by that? It means that while when I multiply my sparse x by phi, I'll get the y. There are infinitely many other x's that when multiplied by phi give the exact same y. Okay, that's what it means to have a null space, right? So this is a bit of a problem. And because of this, it's easy to see that this transformation somehow has to lose information, right? Because it's mapping signals that are different to the exact same set of measurements, never to be able to be unraveled. Okay, but really it's not that bad, because in fact we're not interested in signal acquisition systems for arbitrary data. We're only interested in processing and analyzing and acquiring sparse data. So now let's just think for a second, what happens when x is sparse? Well, that matrix now has a very different flavor, because in fact you can see that y is, in this case, is just the linear combination of 3 columns from phi. Right? Everybody see that? Just tip the vector x up and pick out those columns. Okay, so since we're only interested in sparse vectors, in fact, the structure of phi is entirely different. And in fact, it could have an entirely nice rank, because it's a very tall and very skinny matrix. Okay, as long as k is less than n. Okay, so phi is effectively an m by k matrix. Now, this assumes a lot of things, of course, namely, especially that you know the support of where those large coefficients are. Right? And of course, we're not going to know in practice. But this really gives us a setup of how we might design a processing sensing phi that's good for sparse data. So here's the basic idea. It's the following design problem. Let's design a phi so that no matter which k columns I pull out of phi, right? No matter which k columns I pull out of phi, when I put those together into this m by k matrix, that matrix has full rank, right? Or Nice full rank. And in particular, we'd really like it to be as close as possible to an ortho basis. Right? We'd really like that. So think in the back of your mind, ortho basis. Okay, so that's the design problem. Okay, hopefully everybody sees the design problem. Now let's talk about the geometry behind why this might be actually solvable. So let's go back to talking about sparse signals and the actual signal model that corresponds to sparse signals. So remember, we have an X that's n-dimensional, very, very long. It only has k non-zero entries. And what I want you to think about just for a second is, what does the structure of the set of all sparse signals look like? Okay, if you think for a second, what does the structure of band-limited signals look like? You'll think subspace, right? I'm in n dimensions, and if I can subsample my data, there's some lower dimensional subspace. Well, now you might ask, right, I don't have band-limited signals now, but I have signals where k coordinates are non-zero and all the rest are non-zero. And if you think about this for a minute, it's a very, very interesting set. Okay? And let's just do the example of n equals 3, k equals 2. The basic idea is that the set of all two sparse signals in 3 dimensions correspond to the set of the 3 subspaces of dimension 2 that live aligned with the coordinate axes. Does everybody see that? Okay, a nod of the head. Very, very important, right? So just a couple things. One, it's a union of subspaces. It's not a subspace. It's a union of n choose k subspaces. Two, the subspaces are themselves very closely aligned with the coordinates, right? They don't stick out arbitrarily at weird angles. They're all at essentially 90 degrees from each other. And third, very importantly, this is an extraordinarily nonlinear set. Okay, take any 2 points on this set. If they don't come from the same hyperplane, right, the chord connecting them, the line connecting them, has no signals from the set. So it's extremely non-convex, nonlinear set. Okay, and now your job is to take this 3-dimensional intuition, right, and take it to 10 million dimensions. Right? So everybody close their eyes for a minute, right? And think, I'm in 10 million dimensions, and I have, say, 10,000 dimensional hyperplanes. Right? They're all orthogonal to each other. They're all aligned with the coordinate axes. And there are 10 million choose 10,000 of these hyperplanes. Okay? Very nonlinear set. So what we're talking about when we talk about information preservation is getting around this null space problem. Remember, we have this problem that when we multiply phi times x, there are infinitely many x's that when multiplied by phi give the exact same y. So what we want to do is get around that by preserving the geometry of this set of union of subspaces. And here's how we do it. It's actually very simple. Here's our 10 million dimensional space with our 10,000 dimensional hyperplanes. Take any two signals, any two 10,000 sparse signals, right, in this high dimensional space, and think of their distance. Right? Say they're a certain distance from each other. What we want to ensure is that their measurements, right, if we have x1 and x2, their measurements phi x1 and phi x2 are basically the same distance as x1 and x2 are from each other. I didn't say this very clearly, but I think it should be pretty straightforward. To preserve the geometry of all of these sparse signals, basically we just have to preserve the pointwise distances between any of these points. Why is this relevant? Because if x1 is a picture of Rob and x2 is a picture of me, what we're guaranteed of is if we both stand in front of some kind of compressive acquisition device, we will be able to tell the difference between a picture of me and a picture of Rob. Because phi times Rob and phi times me is about the same distance away as the picture of Rob and the picture of me. Hopefully this makes sense. So this is why we call it information preservation, and we're just trying to preserve the L2 distances. Right? And this has a term in the geometry as basically what's called a stable embedding. That we're going from an n-dimensional space, and this operator phi, this matrix, is going to stably embed this blue sea urchin-like set into this low-dimensional space. So now the question is, can we actually do this? And so how do we translate this geometrical picture into an actual mathematical desideratum? Okay? So here's what it is. Basically, the fundamental idea is this idea called the restricted isometry property, which is exactly what I just said that I was looking for, trying to keep the distance between x1 and x2 the same as phi x1 minus phi x2. Take their quotient, right? And let's ask that no matter which sparse x1 and sparse x2 I have, when I divide the distance between phi x1 and phi x2 by x1 and x2, I get a number that is very close to 1, right? Where delta here is a number very, very close to 0. And the reason why we call it the restricted isometry property of order 2k, a little bit technicality, not that important, but just if x1 and x2 are each k-sparse, then really this distance, the difference vector x1 minus x2 is in general 2k sparse. Right? Because if I subtract a k-sparse signal from a k-sparse signal, the positions won't necessarily coincide. And so in general, that difference vector has length 2k. But it's only a factor of 2 larger than the sparsity of x1 or x2. So then our goal then is to design a phi, not to have this property where I pull k columns out and have that be close to an orthobasis, but the basically same thing. I'm going to pull 2k columns out at a time. Okay, so that's our goal. If we can do this, if we can design a phi such that when I pull 2k columns out of that matrix and pack them into a matrix and look at the rank, if the rank is full, then we actually know that we have a stable embedding, and we preserve all the information in sparse signals when we project to a lower dimensional space. Okay? So this is all we have to do. It's very, very simple. The problem is that it's unfortunately an NP-complete problem. Okay, so it's an extremely hard problem to design such a matrix. As you would just think about it, this is a combinatorial kind of thing. Even verifying that a matrix has this property requires you to test all n choose 2k possible packings of the matrix. Right? So it's horribly difficult. So hopefully that makes sense. So the big insights always come from Russia. So the big insight from Boris Kashin and Gluskin and some others was that rather than try to design this matrix and worry about designing this matrix, let's just pick a random matrix. Just draw a random Gaussian or a random plus minus 1 matrix. Then you can actually show, and this has been known for quite a long time, that phi actually has this full rank property, this restricted isometry property, as long as the number of rows of this matrix is basically linear in k and only logarithmically dependent on n, which is a pretty amazing fact, actually. Okay, it's a pretty amazing fact that says this matrix does not have to have that many rows. Right? It just has to be linear in the number of columns you're pulling out and then logarithmically dependent on n. This log is the thing that really gives us hope. Right? That this idea could be useful for new kinds of data acquisition and processing algorithms to get over these different exponential trends of Moore's law versus the amount of data. Okay? Because the amount of data is n. Just very briefly, just technical aside about how this can be proved, it's really actually not that difficult to show that a matrix has the RIP property. Sketch of the proof, all you do is pick one of the k-dimensional subspaces, intersect that, basically find the unit a unit L2 hypersphere inside that subspace. Then throw basically an epsilon net. Basically throw down a set of points that all are within epsilon of each other within this hyperplane. And then apply a very powerful tool from dimensionality reduction called the Johnson-Lindenstrae lemma, which is stated right there, that says if I have q black points over here, and I project them down with a random matrix, like a random Gaussian matrix, as long as the dimensionality down here, m, is larger than the logarithm of the number of points, right? That's a number that grows very, very slowly. Larger than the logarithm of the number of points, I, in fact, preserve all the point-wise distances between these points in this point cloud. Okay, that's the critical step. Then all you have to do from there is extend from the hypersphere to the entire k-dimensional plane, and then extend by the union bound to all possible hyperplanes. So it's really a pretty mechanistic once you have the Johnson-Lindenstrae lemma to be able to prove these kind of things. And people can clearly see the relationship between these and this kind of construction and all kinds of other packing type constructions from codes, as we will talk about a little bit later. So just summarize then where we are. What we're proposing is some kind of data acquisition or processing system that's based on randomized linear combinations, where now, instead of sampling our data, we're going to measure our data linearly, but we're going to measure it by taking inner products of my data x with random vectors. So each entry of y, the measurements, is just a different randomized linear combination of the entries of x. And what we've just seen is that as long as the number of measurements y is linear in the sparsity, k, and only logarithmically dependent on the length of the vector, we will be able to preserve all of the information in sparse signals and have that preserved in our vector y. Okay, so this is let's call it the encoding problem or the measurement problem. So now let's turn to the recovery problem or the decoding problem. Okay, now we're given a y, and now we want to figure out which x, right, was presented to the acquisition device. This would be like sync interpolation when we do a uniform Shannon type sampling at the Nyquist rate. So now we're given y, we want to get x back. And if we just look at this again totally from a naive standpoint, this is again an ill-posed inverse problem. It's a short, fat matrix. There are infinitely many x's. So how are we going to pick the x that actually was present in front of our acquisition device? And again, we're going to appeal to first the fact that we're not interested in acquiring non-sparse data, and two, we're going to exploit the geometry, again, this exact same union of subspaces geometry of sparse signals to be able to uniquely figure out the correct x that was in front of our acquisition device. Okay? So very briefly, what's the geometry of the recovery problem? Well, the geometry is very, very simple. Okay? We have x, which is our true sparse signal that was presented to our acquisition device. It's been multiplied by a random phi to get y. Okay? Now we want to ask, well, the problem is there are infinitely many x's such that phi equals y, and the structure of that set of the infinitely many x's is a hyperplane. It's a hyperplane of n minus m dimensions, okay? And it's basically the null space of phi translated to the true solution x. And since phi is a random matrix, everybody remember this, since phi is a random matrix, what angle is this hyperplane at? It's at a random angle, okay? It's not straight up and down, or it's at a random kind of oblique angle. So our job then, of course, is solving any inverse problem, is we're going to search through this null space, the green null space, and we're going to try to find the best x, right? This is how we solve inverse problems. And the standard approach would be L2 or least squares. So in a least squares type recovery, the optimization that we propose, or is proposed, is that the signal estimate is just the argmin over all possible x's such that phi x equals y of the L2 energy of the x. So we search all through this green hyperplane, and we look for the lowest energy x. Okay, this is nice because it's totally well understood. There's even a closed form formula for the estimate, right, which is very nice. The problem is it's wrong. Okay, it's always going to be wrong. Okay, with high probability, it will never get the right answer. That makes sense. With high probability, never. Numerical experiment. Here is a 6 sparse signal that's of length 1,000. I multiplied by a random matrix, and then I just did the pseudo-inverse, and this is what I get out. It's basically nothing but Gibbs phenomena. Okay? But you have to ask yourself, why is this the wrong answer? In fact, this is the right answer if least squares is your criterion. Because, in fact, the L2 energy of x hat is much, much smaller than the L2 energy of x. So it's the right answer. It's just the wrong problem. Right? So we might ask, what are some other problems that we could pose that might be able to find the right answer? And, let me just say, why does L2 not work? The reason L2 doesn't work, it's very easy to see from the geometry, because minimizing the energy of our solution, subject to being on the hyperplane, is equivalent to basically blowing up a hypersphere, which is the L2 ball, until it touches the green hyperplane. And then the obvious thing is, since this hyperplane is at a random angle, okay, are we going to touch that hyperplane somewhere near the coordinate axes where the sparse signals live? Of course not, right? Because it's always at a random angle, we're always going to touch somewhere out away from the axes, which is precisely why we have none of the coordinates in x hat 0. Okay? It's precisely because of the random angle of that hyperplane. So another approach that we might think of is sort of very obvious, and it says replace the 2 norm with what's called the 0 norm. Okay? And all that is it just counts, it just takes a vector and counts how many non-zero entries there are. So now the game then is going to be travel through the null space, the green null, translated null space, and ask each x, how sparse are you? Right? And once you've gone through the whole null space, pick the x that was the sparsest. Okay, this seems like a good idea. In fact, finds the right answer. Okay, it's very, very powerful technique. Unfortunately, the algorithm that you need to be able to compute this L0 optimal solution is, in fact, again, an NP-complete problem. Okay, because basically we have to check all of the n-choose k subspaces, and so it's exponentially complex. Okay, so the reason why these guys got the best paper award this year in the IT transactions, Emmanuel Candes, Terry Tao, also wrote some other papers with Justin Romberg on this early on, and David Donahoe, was that they figured out how to combine all of these ideas from sparse approximation, from the random matrix theory, from the nonlinear approximation from Cashin, and were able to figure out that they could convexify that L0 problem to an L1 problem. Okay, basically by changing the norm from an L0 norm to an L1 norm, which is the smallest LP norm that still results in convex LP balls, right? Because LP balls are non-convex when P is less than 1. They're convex when P is greater or equal to 1. And they were basically able to show that this will find the right answer, provided you have this RIP property. And not only that, you can find it with a polynomial time algorithm, in particular linear programming. And the essential idea of underlying the proof is that when we solve the L1 problem now, all we're doing is we're blowing up not an L2 ball, but an L1 ball. And the property of an L1 ball is, unlike the L2 ball, it is pointy, right? It's oriented along the coordinate axis. It's pointy, and as you go to higher and higher dimensions, it's extremely pointy. Okay, it's very hard to visualize, but extremely, extremely pointy. And it's precisely playing around with the dimension of this green hyperplane, the n-m dimensional hyperplane, and the different dimensionalities of the faces of this L1 ball that are used to show that you can actually use an L1 optimization to recover the data with k log n measurements. Okay, so this is the sort of basic underlying theory. Let's just review. We've talked about encoding, the forward problem. Given a sparse signal, how do we acquire that signal and not lose information in it? And we saw that if we use a random matrix of size k log n over k, that we would actually preserve the information in the sparse signals. And then we just talked about the decoding or the recovery problem, that we can actually pull x back out of y, right? Recover it by solving, in this case, a polynomial time linear program. Okay, so hopefully this makes sense to people who haven't seen it before and wasn't too much of a review for people who were at the tutorial yesterday. So let's just go over quickly some of the reasons why this is maybe interesting, and then let's talk about how this is being used. So some hallmarks of this approach. The first is it's a stable approach. I don't have a lot of time to talk about it, but Emmanuel talked about it yesterday. It's stable both under additive noise, and also stable under approximate sparsity. Okay, remember we said that not all images will be exactly sparse, they'll be approximately sparse. Well, you can show that we're numerically stable under these kind of perturbations. The second is that it's very different from the conventional approach. This is a highly asymmetrical theory. Well, it's actually totally the same as the conventional approach, but it's completely the opposite way around. In conventional sensing, we try to build really smart encoders. Your cell phone is very, very smart. Your camera is very, very smart. It's acquiring samples, and then it is doing JPEG or MPEG compression. That requires a lot of smarts. In contrast, the recovery or decoding algorithms are very, very dumb, very, very simple. So what we do is we build sensors with a lot of complexity at the sensor itself. In contrast, using this dimensionality reduction, it's completely reversed. The encoder is completely dumb. Okay? It's only just taking randomized measurements of the data. And all of the smarts, if you will, are in the decoder side. Okay? This is very bad for some applications, but very, very good for other applications. You might think of, for example, just very cheap distributed sensors, right, where you don't want to put a lot of smarts into the sensor. This might make some amount of sense. Another property that's very interesting is because we're randomizing our data by multiplying by a random matrix, okay, we have the property where each individual measurement carries basically the same amount of information, because each measurement is basically an inner product of all the entries of my vector x with a random vector. This is very, very handy for a number of reasons. The first is it makes us very robust to loss and to quantization. Namely, if I'm going to send some packets to Rob, and some are going to get dropped along the way. Some of my measurements are going to get dropped along the way. Well, instead of having to do, for example, heavy error protection, right? If I'm sending, for example, wavelet coefficients or MPEG coefficients, instead I can just calculate how many packets I think he's going to receive and just send an excess of randomized measurements. As long as he gets enough measurements, it doesn't matter which ones, as long as he gets enough, he will be able to perfectly reconstruct the data. And this is basically a fountain code type property that's built in automatically into these measurements. Last two. One, I won't talk very much about encryption, but there's a weak encryption here going on, in that if you don't know the matrix phi, if the packets are intercepted by Vince, right, on their way to Rob, if Vince doesn't know the phi matrix that I use to generate those measurements, it's very hard for him to be able to recover the data. So there's an encryption property. And then finally, there's a universality property that I'd like to just talk about more in a little detail, that basically means the hardware to do this dimensionality reduction can be built completely generically. 10? Okay. Can be built completely generically, meaning that if I have a signal x now that is sparse, not in the space domain, but for example in the DCT domain, then when I multiply that by a random matrix phi, to acquire my measurements y, all I have to do is realize that an IID Gaussian matrix multiplied by any orthogonal matrix is basically going to give me another random Gaussian matrix. So it doesn't matter what basis your data is sparse in, the exact same random measurements can be used no matter what, and you only need to know that sparsifying basis at the end when you're going to do your reconstruction. Okay, so hopefully this makes some sense. And let's talk now about some applications of these ideas, and then talk about some of the relationships with what's going on in exciting developments in information theory. The first thing you can do with random matrices is make a lot of money. So here's a picture by Gerhard Richter. Any Richter fans out there? That we were able to verify that this matrix actually had the restricted isometry property. Because of that, it sold for $3.7 million. Okay, so he claims to have a secret formula that he uses to develop these paintings. So I would challenge you to figure out the secret formula. So the next one I want to talk about besides art is cameras. So let's just talk briefly about a way that you can build a camera using this kind of technology. So this is something we built at Rice with Kevin Kelly a couple years ago. And the idea is, instead of taking the light field from the camera and focusing it on a CCD array, like in a regular digital camera, we instead bounce it off a mirror array, a digital light processing micro mirror device consisting of millions of tiny bacterium-sized mirrors. And these are used all the time in big projectors like that in the back as display devices. But basically, we're turning it around here and using it as a camera by collecting the light that's bounced off that DMD array at a single photodetector, okay, with a second lens. So you can see that this is an optical computer for computing an inner product between the light from the scene X and the pattern that is on that mirror array. And if we put a random pattern on that mirror array, basically what we do at the voltage that we measure at that single photodiode is going to be one measurement of our randomized dimensionality reduction. So by flipping the mirrors m times, we can build up an entire vector y, and we can then use linear programming or other techniques to be able to reconstruct. Okay, so here's our very first pictures that I like to show, just because they're they give you a sense of how well this should work. Here's the target taken with a regular digital camera, 65,000 pixels. Down there, you can see a reconstruction from measurements that are sampled 50 times sub-Nyquist. Okay, so this is 50 times sub-Nyquist acquisition, and you can see it's pretty crappy, but it proves the concept that we can actually recover our signal from those measurements. The second thing that we see is there's a progressivity property that if you're not happy with that picture on the right and you take more measurements, you can actually get a higher quality rendering of your image. And in fact, you can use techniques like cross-validation and other statistical techniques to be able to throttle the amount of measurements to find the sweet spot of how many you actually need for a given data set. Okay, why is this interesting? This is not interesting when companies are coming out with 100 million pixel CCDs. Right? Why would we go to 1 pixel when we could buy 100 megapixel CCDs? Here's why this is interesting. Okay, this is interesting because, well, for the following reason, and people who've heard me talk about this before, don't blurt it out. But does anybody realize why we can very cheaply make a 100 million pixel CCD sensor? Does anybody know why? Okay, it's because of an incredibly lucky coincidence that the same wavelengths our eyes are sensitive to are the wavelengths that silicon is sensitive to. Okay, which means we can bootstrap all of our camera technology on basically RAM technology, which is really the same kind of fabs are used, which is why we can make basically incredibly cheap CCDs. The important thing is once you move outside the visual range, where silicon becomes blind, your $100 camera becomes a $100,000 camera. Okay, very, very quickly. And that's where this kind of technique can be useful. So just three quick examples. One, extreme low light cameras, okay, in the infrared and in the visible. In this case, you have to use a photomultiplier tube to get your measurements. They're like much larger than this, basically the size of a fist. The only people who can afford to build 1 megapixel photomultiplier tube cameras is CERN. Okay, and these cameras cost hundreds of millions of dollars to build. Okay, here's an example of some low light photography using a $500 single pixel, single photomultiplier tube camera. Okay, another example is infrared photography, where cameras can easily cost $200,000. All you have to do is swap out the regular photodiode with a photodiode that's sensitive to infrared radiation. One last example is hyperspectral imaging, which is becoming increasingly important in surveillance, military, and environmental areas, where we're not interested in an RGB color picture anymore of a scene. We're interested in thousands, potentially thousands of colors per pixel to actually be able to get chemical information out of our images. Okay? These are easily gigavoxel, gigapixel type sized data acquisition devices. And this is an area that's just ripe for randomized data acquisition, because we can take into account not only the structure, right, the sparsity structure of the images, but also the correlation as we move from color to color to color to color, to be able to do compression on the order of hundreds to thousands to one, with a very inexpensive camera, where again we just take out the photodiode, put in a spectrometer. We're working with the world's largest maker of disco ball cameras to make disco balls make disco ball cameras. Okay. So let's move into some other areas. I'll just note that there are a lot of other people working in the area of data acquisition devices, actual hardware. And the really important thing is that this idea of dimensionality reduction only makes sense when the measurements are expensive, right? When the measurements are cheap, like you can buy a 100 megapixel CCD for just a couple $100, there's no reason to do this. But when your measurements are really expensive, like a hyperspectral camera, then this can make a lot of sense. Okay, so let me, I pre-cleared a number of ideas to talk about, given that I knew I would run out of time. So let's talk about two, briefly. The first is, how does this apply to detection and estimation problems, which is really the important kind of problems we need to solve data triage type operations. And the second are the relationships with what's going on in information theory right now. So in classification, the important thing to remember is that this CS theory that people have been working so hard on for the last 4 or 5 years is focused almost entirely on the reconstruction end of the data processing menu. But in fact, these ideas are very, very powerful for solving different detection and classification problems. And the really good news is that you can think of randomized measurements as playing a role very much like sufficient statistics for all kinds of different inference problems. Okay, and you know that if you have the sufficient statistics for an inference problem, you can solve it optimally. So we can get close to optimal, near optimal solutions using randomized type algorithms. And let me just give one very, very brief example, and I will dispense with the joke, just given the amount of time that I have. But let's just talk about classification under articulation. This happens all the time. I'm going to have a camera look down on a scene, and I want to tell whether my camera is looking at a tank, a bus, or an SUV. Okay, the problem is that it's never as simple as this. There's always articulation parameters. I don't know the translation. The tank or the bus might have a different translation. It might have a rotation on it. And so there are always L articulation parameters that we need to basically integrate over in some kind of classification scheme. And the standard method to do this is the match filter. That basically you just do standard detection theory or classification theory with it's the GLRT, every possible articulation of the target. Okay? Well, the critical thing is that this is basically kind of like nearest neighbor classification, where I have a piece of test data up there in the upper right, and I'm just computing L2 distances to every possible articulation of a tank, of a bus, and of a SUV. Okay? That's all I'm really doing. Under additive white Gaussian noise, this is the optimal thing to do. Well, the important thing to realize is that in a lot of these articulation problems, these articulated pictures of tanks, buses, and SUVs actually live on a low-dimensional manifold. Okay, so I said there were L articulation parameters. You can actually show that all possible pictures of this bus will live on an L-dimensional manifold in n-dimensional space. Right? And if it's rotation, translation, that's a three-dimensional manifold. That's a very, very low-dimensional problem. And match filter classification then basically becomes the closest manifold search problem. Cutting right to the chase, using the exact same proof techniques that I talked about for sparse signals, you can actually show that you can stably embed low-dimensional manifolds in high-dimensional space into a much lower dimensional space. And the really cool thing is that the exact same formula applies, that the number of measurements, it just has to be linear in the number of articulations and logarithmic in the dimensionality of the data. Okay, so just remember, L might be 3, right? N might be millions, but log n is very, very small. So basically what this says is that we can do our match filter classification directly in the compressive domain. Okay, and let me just give an example. We could either take CS measurements and reconstruct my pictures, and then do match filter classification, or this is saying we can do classification directly on the compressive measurements, much, much lower dimensional. Okay, so that means we never have to do a reconstruction, and it means it can be much, much lower amount of computation in order to solve this problem. Just to give you a sense, this actually works quite well. Here you can see the blue curve and the red curve on the right are what happens to the classification rate as we take more measurements. And those are medium and small amounts of noise. And you see that with even when we have 65,000 pixel images, with as few as 50 or 100 measurements, we're able to do a very, very good job classifying. And we're able to basically localize within about 1 pixel the translation of the target. Okay, so it's completely compressive domain classification. And this extends to a large number of other related problems. Can I take 3 minutes? Talk about encoding? Okay, so let's talk about, because this is something that I think is very, very exciting, that really owes a lot, it owes entirely to results that have been developed in information theory over the last number of years. And let's just talk about encoding and decoding and their costs. Okay, so we talk about this as an encoding, right? This is a pretty good, this is a nice encoding, multiplying an x by a random matrix phi. Okay, we showed that it has this restricted isometry property, it preserves information, is good. Okay, except it's got some practical drawbacks, much like a Shannon code book, right, for encoding, doing error correction coding. It's a dense matrix phi. It's unstructured. It's expensive to apply to X. And since reconstruction algorithms usually involve repeated applications of phi to do the recovery, it also means we're going to have slow decoding. So what can we do that's different? Well, the first thing that might come to mind is some kind of sparse phi. So what if instead of having a dense phi, we have a phi that's mostly zeros, and it just has maybe a few ones, or maybe a few ones and minus ones. Well, this is going to be fast to apply, because each y now is just going to be a sum of a few x's. It might even be fast to decode. The problem is it's not a good phi, right, in the following sense. It's not an information-preserving phi in this restricted isometry L2 sense that we talked about, unless the number of measurements is very large, right? So looked exciting for a minute, but it's disappointing. Okay? But the good news is that by changing our concept of what we mean by stable embedding to an L1, just by changing the norm and saying that I want to preserve L1 distances rather than L2 distances, okay, if we just relax to this, you can actually show a beautiful result showing that if this is your information preservation that you are interested in, then that you can show that you have this property as long as the graph that underlies this matrix phi is an expander graph, right? A kj, 1 minus delta over 2 expander, where j now is just the number of non-zero entries in every given column. So what I mean by that is now we can think of, since phi is a sparse matrix, we can think of it generating a sparse graph that connects x to y. And as long as this graph is an expander graph, we actually have this restricted isometry property in the L1 sense. Okay, so that's a very, very nice result. A number of people have been working on this over the last number of years, and I think this is a very exciting direction for dimensionality reduction work. The second thing is, as soon as we use a sparse phi, now we can apply, much like with LDPC codes, we can apply both message passing algorithms, right, to recover x from y by basically passing messages along this graph. Okay? And again, if this graph is a full graph, like a Gaussian matrix would generate, then it's very difficult to do message passing. But as long as it's a sparse graph, you can actually do it. There are a number of people who've been working on this kind of problem. And the nice thing is that this leads to both fast encoding, so n log n algorithms for going from x to y, and n log squared n algorithms for recovering x from y. Okay? As opposed to n cubed type algorithms for linear programming. And obviously, this is totally connected with all kinds of things going on in LDPC codes, multi-user detection, etc. Okay, so I'm going to wrap up, and just by leaving you with some of the other really interesting open areas in the dimensionality reduction literature that are still open, that are very closely related to the things people are studying in information theory. And let's just go through them really, really briefly. We talked a lot today about measurement recovery. This is really all about coding over the real numbers now, rather than over a finite field. Rob Calderbank's done some really interesting work in the last couple of years, actually. Well, a number of years, but especially the last few years, trying to work with these kind of coding problems. Something I haven't talked about at all is finite rate of innovation sampling coming out of Martin Vetterli's group, which is very closely related to real-valued Reed-Solomon codes and Vandermonde matrices. Okay, so there's very, very beautiful interconnections there. There's a theory for multi-signal compressive sensing that is very related to Sleppy and Wolf, with the same kind of trade-offs of a sum rate bound, right? And a little nip taken out of the coding rates. I haven't talked at all about greedy recovery algorithms, but these are very related, identically in many cases, to what people are using already in multi-user detection type problems and other kind of multi-class detection problems. And finally, this democracy problem that I already mentioned is very closely related to what's going on today with fountain codes. Okay? So I think I'm going to end, but I just want to say one last thing. Things I haven't covered at all in this talk, just to pay tribute to some very, very important parts of work. The first, I haven't said anything about finite rate of innovation sampling, and I would highly recommend people look into this. I haven't talked at all about random or coset sampling, which is a very closely related but distinct theory, and I haven't talked at all about these greedy recovery algorithms just because of time. So let me just end there by a quick summary. So we've talked about this idea of randomized dimensionality reduction or compressive sensing. We've talked about how it enables us to combine the idea of sensing, compression, processing, analysis all into one system. It works because we have this preservation of geometry property of sparse signals. And there are clearly many, many interconnections with information theory. So I think I'm ready to take questions. I'm going to just point people to the community website if you're interested in learning more about this field. We've just passed, I think, 350 papers. So if you're interested in learning more about compressed sensing, please go to this website. And if you work on the area and you're interested in contributing, just send us an email and you can contribute. And I think while the questions are up, I'm just going to throw up my obligatory connection slide and say that if anybody wants to get involved in changing the world, then please talk to me after the talk. Thank you very much.
Okay, some comments from an information theoretic lens. In information theory, we like to answer questions like what is possible, but we also like to pose the question, what is impossible, what we call converses. And we also like to do that without putting constraints like linearity in our encoders. So I wonder if there are any results along that direction in compressed sensing, and also whether there are results that assume that your signal model is more informative than just the sparsity, deterministic model.
So, well, I guess everybody heard the question. Really, really good question. And actually, I'm going to ask if I could have my slides, because I'll show a picture. I would say that the current theory that I talked about is completely based on this linearity assumption of the measurements. And I think that this is something that we really need to break out of, because I think nonlinear measurements, as we all know, are potentially far more powerful than linear measurements. And I think that we have to break out of it first because we should probably be able to do, I think, even better. We should be able to take even fewer measurements. And second, one of the ideas that I really didn't talk about at all in this talk is that everything I talked about is a real valued theory. And if we're going to actually transmit any of these measurements, we have to quantize. And so treating the theory as I'm going to do linear measurement followed by scalar quantization is really that doesn't really sit well with me. And I think we really need a theory that combines real valued in with discrete time out, or finite field out. Does that make sense? And just an example for that. So just let me say the other real area that we need to move from is this entirely simplistic model of sparsity, right? And we need to start realizing that in addition to a primary structure of sparsity, real data has incredible powerful correlation structure. And we need to be able to incorporate that into this dimensionality structure. And the good news is that for a large class of different correlation models, you can extend all of the theory. And that's the thing I dumped from the talk because I was running out of time, but I could speak with you after about it. The great news is that in some cases you can do far, far better by taking into account the fact that there's correlation structure in your data in addition to just the simplistic sparsity structure. And this is what we need to actually compress when we sense, right? Because JPEG and JPEG 2000 and other compression algorithms take into account much more subtle structure than these models that I talked about for most of the talk. The good news is, though, I think we have made progress on this.
Okay. I think I wasn't expecting quite such a long question.
Well, it was a deep question.
It was a very deep question. I think we have one more quick question from the floor here.
I hope it will be quick.
Yeah.
So in talking about compressed sensing versus, say, the conventional approach,
Sure.
we talk about dumb sensors versus smart sensors,
Sure.
dumb decoders versus smart decoders. But I'm wondering if there's a way to trade off between the complexities at the two ends.
Oh,
so
really
for
good
example,
point.
for the single pixel camera,
Totally.
you argue that, okay, I can take many more measurements and I'll improve my performance. Can I have a 4-pixel camera and therefore
Totally.
need less
Yeah.
measurements?
So I'll answer quick. It's really good. That's a deep question as well. There's two answers. The first is the amount of multiplexing is variable. So in that example, I pushed everything to one single sensor. But if you had a 4-pixel sensor, you could do a 4-pixel camera. So that's taken into account in the theory. I think the other side of your question, though, that is much deeper, is there's some really interesting results linking really Shannon sampling on one side, this randomized sampling, dumb sampling on the other side, with ideas from active learning, which is and adaptive sampling. Guys like Rob Nowak have done some really interesting work in this, and people from the active learning community, of trying to actually say, well, maybe I'm learning something as I'm taking these measurements. I should incorporate that into my model. And they can do very, very good job at image-based sampling and signal-based sampling. So that's a really good question.
Okay.
Okay, thanks, everybody.
So let's thank